Hello. This will be the final video in the series of videos on rate law, and kinetics. And this video will have to do with elementary reactions. So in the beginning, when we reviewed rates and rate law, it was a little confusing why you couldn't just say the rate law was whatever the reactants were raised to the coefficients in the reaction. That seemed like it should be what it is. But these elementary reactions are going to explain why we were not able to do that. So some reactions, though they appear to be one step, actually consists of two or more elementary reactions. So here is an example of one of those types of reactions. So the reaction of 2N2O to give 2N2 plus O2. This actually consists of two steps. In step 1, N2O, I'll put reactant constant 1 there, K1, yields N2 plus O. So rate constant K1 for this step. Then step 2 is N2O plus O to give N2 plus O2. And I'll put K2 as the rate constant there. If you add these two together, the O's cancel each other out. Right? That cancels, and you get 2N2O gives 2N2 plus O2. However, one of these steps is a lot slower than the other one. In this case, the first elementary reaction is slow, and the second one is fast. Another word for the slow step would be the rate determining, or sometimes the rate limiting step. That means that the rate law is determined solely by this first step, this rate determining step. So in this case, the rate law would be as follows. Rate is equal to K1 times the concentration of N2O. That is your rate. Because this reaction has now been broken down into the elementary steps, and we know step 1 is the slow rate determining step, we can get the rate law from these elementary reactions. But we can't from the overall one, because if we tried to do it this way for the overall one, we would have N2O raised to the second power. But N2O is only unimolecular here, raised to the first. So that's why we have to use that elementary step. Now, you can also have the rate limiting step not be the first step of the reaction. So here's another example. We have 2NO plus Br2 to give 2NO-Br. This consists of two steps. In step 1, NO reacts with Br2 in equilibrium. So we'll have a K1, and then the reverse would be K to the minus 1 to give NO-Br2. And then in step 2, NO-Br2 plus NO gives 2NO-Br. So immediately we can see this NOBr2 is an intermediate. Now for this one, step 1 is the fast and step 2 is the slow. So based on what we did last time, we would say then that rate is equal to K2 times the concentration of NOBr2 times the concentration of NO. However, NOBr2 is an intermediate. It doesn't appear in the overall reaction. So we cannot leave NOBr2 in the rate law. So what we have to do is look back to the first step. In step 1, rate is equal to K times NO times Br2, right? This K specifically would be K1, and that's equal to K to the minus 1 times NO Br2. So if we divide each side by K to the minus 1, we'll get that the concentration of NO Br2 is equal to K to the 1 over K to the minus 1 times concentration of NO times concentration of Br2. Now, this can plug in to the NOBr2 there. So now we'll get that rate is equal to K2 times K1 over K to the minus 1 times NO times Br2 times NO. Now we can simplify this. We can take all of these K's and make it into a new K. We have two NOs, so this would be NO squared times Br2, and this would be our rate law when the second step is the rate determining step.